All right, guys, so this is Unit 3. This is going to be the second review video on derivatives. I think there's a total of 3 or 4 of these videos on differentiation. So the topics we're going to address are these today: composite functions, implicit functions, and inverse functions. So let's go ahead and get started. Make sure you guys are filling in the blanks on your notes. And once again, I do encourage you guys to print these out. Writing all this by hand would be quite tedious. So print it out and just fill in the blanks. That'll make life a little bit easier. So we're going to start off by talking about the chain rule here. The chain rule is used to find the derivative of a composite function. A composite function is a function that is defined by one function being plugged into another. So for instance, h is a composite function because h is this. One function being plugged into another function. And so the way that we find the derivative of a composite function is with the chain rule. All right, and so what is the chain rule? When you want to take the derivative of a composite function, you do the derivative of the outside function, which in this case is the f, and you multiply it by the derivative of the inside function, which is the g. Okay, so the derivative of the f function looks like this in this case, and the g just stays the same. And then we multiply that by the derivative of the inside, which is the derivative of g. Okay, now sometimes you can have a double chain rule. So if your composite function is a composite of a composite, in other words, we have of h is plugged into g, which is plugged into f, then you just do the double chain rule. Okay, so we have, and I compared these a while back when we first learned this to an egg. You have the shell of the egg, you have the yolk of the egg, which is the function that's deepest inside, and then the other part, which I guess I'll just do in green here, is the egg whites. Okay, but it's still the same idea. You do the derivative of the shell, keep the inside the same, multiplied by the derivative of the egg whites, keep its inside the same, multiplied by the derivative of the yolk. And that's it. So that would be like a double chain rule. Okay, so that'll come up in our lesson this week. Another thing that will come up is higher order derivatives, meaning derivatives that are more than just the first derivative. So if you have a function, f of x equals y, the first derivative, as you already know, looks like this and this. We've talked about that in this past week gone by, and we've been doing it all year. But the second derivative, here's how you'd represent that. You can find the second derivative by taking the derivative of your first derivative. So if this is x squared, if that's my original function, the first derivative would be 2x, and the second derivative would be the derivative of this, which is 2. So you can just keep taking derivatives over and over again. So the second derivative looks like this, the third derivative looks like this, or if you're using this notation, they look like this. And a little subtle detail to pay attention to if you're going to be using these ones is notice where they put the numbers. On the top, the 2 goes in between the d and the y, and on the bottom it goes outside the x. Okay, so keep that in mind. That's the notation for those other derivatives. All right, so let's talk about implicit functions right now. To begin with, let's talk about explicit function. An explicit function is a function where the output variable, y, is isolated. It's all by itself. In other words, y equals, and you have the rest of the function. So y is all by itself over here on the left side of the equal sign. Well, an implicit function is one where the output variable is not isolated, so like this. Now this equation here is actually the same equation as this, they're just written differently. This one down here is written in implicit form, and this one up here is written in explicit form. So finding the derivative of an implicit function has quite a few steps to it. First of all, if the variable of the expression you are differentiated to matches the variable of differentiation, you find the derivative like usual. So for instance, let's say I'm finding the derivative with respect to x of x squared. Well, that would just be 2x, nothing special. Okay? And the reason for that is because the variable of integration, I'm sorry, differentiation, x, matches this variable of the expression I'm doing. So whenever these two things match, you just do the derivative like normal, okay? But if the variable of the expression you're differentiating doesn't match the variable of differentiation, then we have to apply the chain rule, which usually means we're just going to end up putting a y prime there. So let me show you what I mean. Notice here that we are taking the derivative with respect to x of y cubed. Now notice that this variable here doesn't match this variable. So you still take the derivative like normal, move the 3 to the front, take 1 off the power. That's the power rule, right? But notice now we have an extra little thing added here, a y prime. And that's because these variables don't match. And what you're really doing is you're doing a chain rule. That's why that's there. We're thinking of the outside function here as something being cubed, and we're thinking of the inside function as the y. So this is like the derivative of the outside here, the 3y squared, the green part, and the derivative of the inside is the y prime. So you're doing the chain rule there. So to review, if this letter matches this letter, just take the derivative like normal. If they don't match, then after you take the derivative like normal, put a y prime next to it. Now, it's not always going to be y, though, just so you know. If this were an a, for instance, then it would be 3a squared times a prime. So it's whatever is here that goes here, all right? All right, let's go ahead and continue onward. So that's the first two steps. Now, if after doing that, you're going to have a y prime in there somewhere. So if there's more than one of these y primes, then you're going to want to put all your y primes on one side of the equation and everything else on the other side. And then you're going to factor out the y primes. If there's only one y prime, you can kind of just skip to step 4. Okay? But if there's more than one y prime, move all the y primes to one side of the equation and move everything else to the other, and you're going to have to factor out the y prime before you move on to step 4. Let's go ahead and take a look at step 4. After that, you just get y prime by itself and you're done. You have to simplify usually. So let's take a look at an example. So here's an example. This is an implicit function. Why? Because my input variable is a, and that's in there, and that's okay to be in there, but notice that the output variable b is buried inside the equation also. So this is an implicit function, and because of that, we're going to be doing implicit differentiation. So the first thing we do is we're going to take the derivative. Now, anytime this letter matches the letter of the expression, you take the derivative as usual. But anytime this letter does not match the letter of the thing you're taking the derivative of, you're going to get a prime. So for instance, on this one, I'm going to get a b prime out of it. So let's take a look at our first outcome there. If I were to apply those first two steps, I would end up with this. The derivative of 3a squared is 6a. The derivative of negative 4b, well, the derivative of negative 4b would just be 4, but we need to put a b prime there because they didn't match. The derivative of 2 is 0. The derivative of 8b squared, just take the derivative like usual, you get 16b, but since the b doesn't match the a, you get a b prime. And then finally, the derivative of this one, you just get negative 6, and that's because the a matches the a, so you just take the derivative like normal. All right, so that's step 1. And finally, oh, also the 1 over here just disappears because it's a constant. Step 2. Step 3 is to take all of your b primes and move them to one side. So I put them on the right side of the equal sign, and everything else you put on the left side. Or it doesn't matter what side you put them on. All that matters, you put all the primes on one side and all the non-primes on the other. Okay? After that, you have to factor out the b prime. So notice how both these terms here have a b prime, so you factor it out. After that, you're able to get b prime by itself by just division, and you may have to simplify. So in this case, all of these can be divided by 2, so I would reduce it. And there's your final answer of getting b prime. Okay, so there's how you do it. Now let's talk about how to find the second derivative of an implicit function. We talked a little while back about higher order derivatives, which was right here. Well, if you can find the first derivative, you can find the second derivative. Well, to find the second derivative of an implicit function, the first thing you do is just do what we just did. Find the first derivative by using this last slide here, slide D, to find the first derivative. Then you repeat it to find the second derivative. But you'll find that in the process of repeating that, you're going to end up with some y primes in the second derivative. And this is where you do have to do something a little bit different. You're going to replace all the y primes with the first derivative from step 1. Okay, so that's how you find a second derivative and simplify it. So let's take a look at a new concept now. We'll talk about the derivative of an inverse function. First of all, what is an inverse function? Two functions, f and f with a little -1 here, are inverses if f of a equals b implies that f inverse of b equals a. In other words, their outputs are swapped. Outputs and inputs are swapped around. Okay, that's what makes an inverse function an inverse function. Now, the derivative of an inverse function, let's say at x equals b, is given by this little formula here. So the derivative of the inverse is 1 over the original function, not the inverse, but the original function prime of the inverse function at b. And here's our steps on how to find the derivative of an inverse function. Okay, there's quite a bit associated with it. Usually what they're going to do is they're going to tell you that, okay, f of a equals b. They're going to give you some initial condition where x is this and y is this. What we need to do with that for step 2 is we need to write that somewhere on our paper. Oh, so if f of a equals b, that means f inverse of b must equal a. So you'll want to write that somewhere on your paper just to keep it in mind. Then you're going to write the derivative rule out. So since we're trying to find the derivative of an inverse, you're going to write this thing. Now, the next thing we're going to do is we're going to replace the f inverse of b in our formula. You're going to replace this with a. Now, what do I mean by that? Well, back here in step 2, we said that f inverse of b equals a. So that means you could replace f inverse of b with a, and you get this now as a result. The next thing you're going to do after that is you're going to find f prime of a. In other words, what does this equal? That's a two-step process. You're going to have to find the derivative of the original function, and then you're going to plug the a value into it. After you have that answer, just plug it in here for the f prime of a, and you've got your answer. And that's the end of it. So here's an example of finding the derivative of an inverse. Now, as I mentioned on step 1, they give you something like this, f of 2 equals 1. So step 1 is, f of 2 equals 1. So from step 2 then, that means we can conclude that f inverse of 1 equals 2. Step 3, we want to write out our little formula here. We're trying to find f inverse prime of 1. So f inverse prime of 1 is equal to 1 over f prime of f inverse of 1. The next step is we're going to replace f inverse of 1 with 2. Why? Because f inverse of 1 is 2. Step 4, we want to find out what f prime of 2 is. So the first step there is to take the derivative of the original function. So the derivative of f of x here is 3x squared minus 4. And then to find f prime of 2, we simply plug in 2, which gives me 8. Now that I know that, f prime of 2 equals 8, we can do step 6 and just replace f prime of 2 with 8 and see that our final answer is 1/8. So that's the process for finding the derivative of an inverse. Also in this particular section or lesson set is we're going to be doing the derivatives of the inverse trig functions, also known as the arc trig functions. And this is just something you have to memorize. You know, the derivative of arc sine of u is the derivative of the inside on top and square root of 1 minus the inside squared. Something to take note of is that sine and cosine are almost identical. The only difference is that cosine is negative. That relationship holds also for tangent and cotangent. They're identical. The difference is that cotangent has a negative on it. And also for secant and cosecant, they're identical. It's just they have opposite signs. So almost every one of these problems will have the chain rule built into them, just so you know. They're going to have an inside function, and it's the derivative of the outside, which is the formula, times the derivative of the inside, which usually just ends up going on the top. So the chain rule puts the derivative of the inside on the top of this fraction. All right, so let's move on here. Next thing we'll talk about here is the mean value theorem. We've talked about this last week also, but we're going to go into a little more detail this week with it. If f of x is continuous on the closed interval and differentiable on the open interval, this means endpoints are included, this means endpoints are not included, then there must be at least one value, x equals c, such that the instantaneous rate of change is equal to the average rate of change. And we talked about this last week as well, but I'll redraw the picture. So if we're going from A to B, the average rate of change, oh, this is supposed to say A. I'll fix that on your guys' notes. But the average rate of change is the slope of the secant line, f of b minus f of a over b minus a. So I'll draw a secant line there. And according to this theorem, so long as this function is continuous, meaning there's no holes, gaps, or jumps, and differentiable, meaning there's no cusps or vertical tangent lines, then somewhere along this curve, there has to be at least one place where the tangent line, that's the slope, that's the derivative, is parallel to it. So like, for instance, I would say like maybe right here, we have one, and right here, we probably have one as well, okay? And probably somewhere up here, there's one as well, right before it gets to the endpoint. So it looks to me like there's 1, 2, and 3 places where there is a c value where the instantaneous rate of change, or the slope of the tangent line, is equal to the average rate of change, or in other words, parallel to the average, or the secant line, okay? And so that is the mean value theorem. Now let's talk about a few ways that that question can be asked. There are 3 pretty common ways that it's asked. One of those is when you're dealing with a graph. When you're dealing with a graph, they'll typically ask you how many values of c on the interval from a to b are there, where, and that's going to be worded a few ways. I'd say the most common way it's worded is like this. How many values of c on the interval ab are there where the instantaneous rate of change is equal to the average rate of change? Or another way they may ask it is, how many values of c on the interval ab are there where the mean value theorem is satisfied? Or I think a less common way, but it's possible, is they may say, how many values of c on the interval ab are there where the tangent line is parallel to the secant line? And the reason I don't think they're going to ask it that way is because it makes the question a little bit too easy. It's a little bit more obvious that way. So I'd say this one up here is the most common way they're going to ask it, the first one. But all 3 of them mean the same thing. Take your graph and sketch a secant line, and then ask yourself, how many places along this curve can I make a tangent line that's parallel to that? Well, it looks like there's one here, maybe one here, and probably one like way close to the top up here where the tangent line would be parallel to that. And so the answer to this question here is 3. There are 3 places where we can get a tangent line that's like that. And it's not too uncommon for that answer to match the number of humps that this graph has. There's one hump here, one hump here, and one hump here. And just so you guys know, that doesn't mean the tangent line is on at that hump. Like it's not at the very top here. It's actually a little bit more off to the side. It just means that as many times as this graph turns around, that creates a new opportunity for that tangent line to repeat itself. Okay, but there it is. All right, let's go ahead and move on to a second way that the mean value theorem can be asked, and that's with tables. And this can also apply to graphs as well. The question, instead of them asking you how many places does it occur, they may just say, does it occur? Is there a value c such that f prime of c equals some number on AV? So if they ask it that way, first of all, you want to make sure that the function is differentiable and continuous. If it is, then we can say that since f of x is differentiable on the interval ab and continuous on the interval ab, there must be some value c such that this. And you just plug the numbers in that they give you, and you work it out, and it should end up equaling the number that they give you here. Okay, so you do need to show your work for these types of questions. So when you're doing these types of questions where they ask you, is it possible that the mean value theorem applies, step 1 is to make sure that it is differentiable and continuous, and step 2 is to basically just state this whole thing and make sure you show your work as you go. All right, let's move on to a third way the MVT question can be asked, and that's if they're giving you an equation. So they might give you some equation, like they'll say, f of x is equal to x squared minus 5x plus 3, and they're going to say find all values x equals c such that the mean value theorem can apply to it. Okay, so basically we just want to get our mean value theorem up there, which is where the instantaneous rate is equal to the average rate. So your first two steps in this process is to find the derivative of the function they give you, then find your average rate of change by plugging in the two endpoints that they give you, and then make these two pieces equal to each other, and then solve for x. And that'll tell you all the places where the mean value theorem is satisfied. So that's another way that the mean value theorem may be asked. Pretty common type of question. But that does it for this video. So we'll see you guys later, and hopefully that was helpful. Have a good one.